In this video, we're going to transition from lexical analysis to parsing and talk a little bit about the relationship between those two compiler phases. We've already talked about regular languages, and it's worth mentioning that these are the weakest formal languages that are widely used, but they have, of course, many applications, some of which we saw in previous videos. Now, the difficulty with regular languages is that a lot of languages are simply not regular, and there are some pretty important languages that can't be expressed using regular expressions or finite automata. So let's consider this language, which is the set of all balanced parentheses. So some elements of this language would be the string 1 open paren, 1 closed paren, 2 open parens, 2 closed parens, 3 open parens, 3 closed parens, and so on. And you can imagine that this is actually something that's fairly representative of lots of programming language constructs. So, for example, any kind of nested arithmetic expression would fit into this class, but also things like nested if-then-elses will have this characteristic. And here, with the nested if-then-else, it's just the if statement that functions like an open paren. Not every language is like Cool, which has the explicit closing phi as well, but they're implicit in many languages. And so there's lots of nesting structure in programming languages constructs, and those cannot be handled by regular expressions. So this raises the question of what the regular languages can express and why they aren't sufficient for recognizing arbitrary nesting structure. So we can illustrate the limitations of regular languages and finite automaton by looking at a simple two-state machine. So let's consider this machine. We have start state, and then the other state is the accepting state. And we'll have this machine just be a machine that we've already seen, actually, and it'll recognize strings with odd numbers of ones. So if we see a 1 and we're in the start state, we move. We've now seen an odd number of ones, we move to the accepting state, and we stay there until we see another one, in which case we've seen an even number of ones, and then we're in the start state. So whenever we see an odd number of ones, we're in the final state. Whenever we see an even number of ones, we're in the start state. And if we feed this a fairly long string of ones, let's select something with 7 ones in it, then what's it going to do? It's going to go back and forth between these states, and it's going to wind up in the final state when it gets to the last one, so it'll accept. But notice that it doesn't know how many times it's been to that final state. It doesn't remember the length of the string. It doesn't have any way of counting how many characters the string had in it. And in fact, all it can count here is the parity. So in general, finite automata can really only express things where you can count modulo some k. So they can count mod k, for some k, where k is the number of states in the machine. And so, if I have 3 states in the machine, I can keep track of whether the string length is divisible by 3 or some other similar property. But I can't do things like count to an arbitrary I. So if I need to recognize a language that requires counting arbitrarily high, like recognizing all strings of balanced parentheses, you can't do that with a finite set of states. So what does the parser do? It takes the sequence of tokens as input from the lexer, and it produces a parse tree of the program. And for example, in Cool, here's a input expression that is input to the lexical analyzer. The lexical analyzer produces this sequence of tokens as its output. That's the input to the parser. And then the parser produces this parse tree, where the nesting structure has been made explicit. So we have the if-then-else, and then the 3 components, the predicate, the then branch, and the else branch of the if. To summarize, the lexer takes a string of characters as input and produces a string of tokens as output. That string of tokens is the input to the parser, which takes the string of tokens and produces a parse tree of the program. It's worth mentioning a couple of things here. First of all, sometimes the parse tree is only implicit. So the compiler may never actually build the full parse tree. We'll talk more about that later. Many compilers do build an explicit parse tree, but many do not. The other thing that's worth mentioning is that there are compilers that do combine these two phases into one, where everything is done by the parser. So the parsing technology is generally powerful enough to express lexical analysis in addition to parsing. But most compilers still divide up the work this way because regular expressions are such a good match for lexical analysis, and then the parsing is handled separately.